just to give you an idea about my background, I did my PhD on learning theory, statistical learning theory. That was in France, and then I went to the Max Planck Institute for my postdoc, and after that I got a bit, how to say that, bored with theory, I would say, and I started to be interested in applications of machine learning, and that's why I went to this company, Pertinence, which is a software company that sells machine learning software, essentially, to people in the industry. But still, I think there is a value in being interested in actual problems, in the sense that it inspires you even for theoretical work. And actually, I mean, this lecture, I'm trying something new here, in a way. I've done lectures like this in the past, and they were mainly oriented at providing results and showing how to prove things and so on. And I realized that it took me a long time to understand the concepts, while it was quite easy, I would say, to follow the actual details of the computations. So, I mean, if you look at the books or the papers that exist, you can easily understand. You need to work the details out, but you can easily understand these details. But to get the full picture is a much harder task. And that's why I decided to give a lecture where I keep the level of detail as low as possible. And maybe it will be, although it's about learning theory, maybe it will be one of the lectures which has a less mathematical display content, the least mathematical display content. But at the same time, I'll try to convey some messages that I think are important. And once you grasp these messages, hopefully it will be easy for you to go and read the papers that are around and understand the details. So I'll try to be as slow as possible, and please interrupt me if anything is unclear and if you want to react on something, because I will make some statements in this lecture, and you don't have to agree with me, and I hope it will be as interactive as possible. So is this loud enough? Do people in the back hear me well? Okay, otherwise I can use the microphone. Okay, so here is the outline of the lecture. There are essentially 3 parts. The first one, which I think is the most important in a way, is where I will discuss about mainly philosophical issues in a way. And I will try to explain why it's interesting to look at learning theory, why is it needed to have a theory of learning, and what does it mean to build such a theory. The second part will be more showing an example or an instantiation of this theory in a specific context of statistical learning theory. And I'll give you some small details about it. And then I'll try to, again, come to concepts and show how to use the results that we will prove in the second part in actually building algorithms. Because I think that's the ultimate goal of this theory, to help people build better algorithms. So the goal of this course will be, as I said before, to give you some ideas, keep things as simple as possible, and insist mainly on the phenomena rather than on the results. Okay, so I'm sorry, but I might repeat things several times, because I like to make sure that everybody understands the messages. So please forgive me if I repeat things too many times. There will be many things that will not be covered, of course, in this lecture. Especially, I will try to avoid as much as possible to give an historical perspective, because most often things develop in a way that is not the most natural way. And it's only after some time, when things settle down, that you start to understand and you see that actually the actual historical way things evolved was not the right one in a way. So that's why I want to avoid it. I will not give you many general results or detailed proofs, and I will avoid most recent topics in this field. Okay, I hope despite this fact, it will still be interesting to you. So first, I'd like to try to define what is a theory in very abstract words. So this is a definition you can find on the web, for example, and I think it has all the necessary ingredients. So a theory essentially is a set of statements that try to explain some phenomena. And one distinctive feature of interesting theories is that they can be tested. So the goal is not only to explain a phenomenon, but also to provide a way to make predictions about this phenomenon in the future. So understanding something theoretically means being able to explain what you have observed so far and being able to predict what you could observe later on. Okay, so these three ingredients: model something, understand it via the model, and use the model to make predictions. And that's what learning theory should do. And the phenomenon of interest here is the phenomenon of learning. Some more definitions, and that will take us to what is the definition of learning itself. It's interesting to look at the definition of induction. I take induction as an equivalent of learning, in a way. And it's nice to compare induction with deduction. So deduction is the process of starting from axioms or initial statements and deducing some new statements by combining these initial statements. And there are certain rules that people agree on for combining these statements in the beginning. And once these rules are agreed upon, you can create new statements. Okay, that's how you prove theorems in mathematics. You agree on the axioms, you agree on how you combine these axioms, and then you go ahead and prove theorems, and there is no question about whether your proof is fine or not. What? Sorry. So that's deduction. Now, induction is somehow going the other way around. You start from a set of statements, and you try to infer the general principles from which you could deduce these statements. Okay, so you start from actual instances or actual observations, and you try to construct the axioms or principles. And that's how physicists mainly work. And that's how they create theories from observing natural phenomena. Okay. Okay. Just as a note, you can also define transduction as the principle from going from observation to new observations directly without going through the axioms. Okay. So now, is there a principle for what should be a good theory? There are some guidance. I mean, you cannot say it's a matter of taste mainly what is a good theory or not. But here is some guidance. The idea is a good theory should be as simple as possible so that it can explain a lot of things with a few principles, right? And these principles, usually you call them assumptions. An example of such assumptions that are quite powerful is, for example, the principle of relativity in physics. From this very simple statement here, you can deduce a lot of laws, physics laws, and make a lot of predictions about how physical systems will behave. And that's what makes it nice. In a way, it's very simple, yet very powerful. But the problem is that these assumptions, statements like this, you cannot really prove them. What you can do is deduce things from them and check that they are true in your experiments. And that's the only, and you can only show that they are wrong when you obtain some conclusion that is not, that doesn't match with the experiment, but you cannot prove that they are correct, right? And that's something to keep in mind. You can only disprove a theory by showing a counterexample, but you can never prove that the theory is correct.
So are you distinguishing between axioms same assumptions, or is it the same?
Well, so far I make it the same. Okay, now we go to the definition of learning. Okay, again, that's something you can find on the web, and it's quite general and abstract. So the learning is to gain knowledge, comprehension, or mastery of something, some skill, through experience or study. And this definition includes actually two ways of learning. One is learning by studying, which I think is not what we are after here, which is, okay, you read something and you memorize it, and then you know it, you have acquired knowledge. But that's not really what we talk about when we talk about learning. It's mainly learning by experience. So essentially what is important is that the knowledge that you gain is different from the knowledge that you received in the learning process. In the practical examples of machine learning, you receive example and you build a model, which is a function. So it's essentially different from what you have observed. You observed finite set of instances, and you construct kind of an infinite object, a function that is defined on every point in your space. And it's because it's essentially different and fundamentally different that the learning process is interesting. You create something different from what you had, from what you started from. Okay? So I will not make many distinctions, and I will take all these words as being synonymous in a way. So I might use them indistinctively. And that's where you start to see that there is something funny here when we talk about learning theory, because I've just defined learning as induction. So the fact that you create some general statement from particular observations, and that's also what creating a theory is about. So learning and creating theory are the same thing. So how can we talk about learning theory? It means we have to make a theory about making theories. So it's kind of a circular process here. And that's why it's, I think it's an interesting topic, because it's really fundamental if you see it like this, because the process of learning underlies most of the sciences, at least. For example, physics, most of physics is building theories. So once we know how to build theories, then we can do physics in a way. So studying learning theory is good, it can be helpful for studying physics in a way. Okay. Okay, so this is a rephrasing of what I just said. So induction is the process of building theories. Learning theories' main focus is induction, which is also building theories. So how can we do it? So there are, of course, we can talk hours about this topic, because there are lots of philosophical issues regarding whether this is possible at all, or whether this makes sense. And I will try not to go too much into these philosophical issues, but give you some ideas. Okay. Now, why would we do that? Why would we study learning theory? Okay, this is kind of a joke. I'm not saying this is a justification for doing it. It's just I like this quote. But the real motivation is here. We want to understand systems that learn from data, right? We want to understand why are the algorithms that we have been studying in this place here, for example, in the last week or so, why do they work at all? And when would they work and when would they not work? Provide a framework for studying their properties, and also being able to formulate predictions. So once we have created a theory, as I said before, a theory is a model that you can use to make predictions. And in this context, it means prediction in here means being able to tell that such an algorithm should be good in such a context or not. Okay? And of course, the ultimate goal is help design better algorithms. Okay, so coming back to this distinction between induction and deduction, there is a fundamental difference, which is that deduction somehow, there is no argument about whether it's fine or not to do deduction, because once you have agreed on the rules, you just apply the rules. For induction, it's completely different, and you can argue hours, and actually you cannot really justify what induction does. Because justifying induction means you have to say these axioms are correct or these axioms are true, and axioms, they don't have to be true or wrong. They are there because you decide they are there, right? So unfortunately, there is no real justification for induction. So I will not give you a proof that some learning algorithm is good or not, because that's not possible. So we'll see what can be proven and what cannot be proven. So to give you some examples, here is a very classical example. Say you observe every morning, you wake up and you observe that the sun rises, and someone asks you the question, so how likely is it, do you think, that the sun will rise again tomorrow? You observed the sun rising every day for d days, for example, and you want to predict how likely it is that the sun will rise again tomorrow. So there can be plenty of different answers to that question, and here are a few. One answer would be, well, I cannot say anything because tomorrow is not like today. So why should I be able to predict something for a new day which is not the same as the ones that I have observed? Okay, that's a bit pessimistic. Or the optimistic statement would be to say, well, it's always rised, so why would it not rise tomorrow? So probability is 1. Okay? And actually, anything in between 0 and 1, or not replying and 1, is fine. That's annoying. Do you know how to? Yeah, but maybe it's because it has some new. It wants me to install new software. Okay. Yeah, so you can also, like, there are some people would give you such an answer here, and that would be obtained from Bayes rules. I guess you mostly know what this is, but I can give you the details. Essentially, you postulate that initially there is some kind of uniform probability of rising and not rising. So 1/2 probability of rising and 1/2 probability of not rising. And as time goes, you update this probability. So every time you observe that the sun rises, you increase this probability a little bit. And when d equals 0, your probability is 1/2. And when d increases, then your probability goes to 1. Okay? So that's also a reasonable thing to do. Every time you observe that the sun rises, you become more confident that it will rise again the next day. Or you can take a more kind of pragmatic approach and say, in what sense is this sun that we have similar to other stars in the galaxy or beyond in the universe? And you can measure the lifespan of these stars and say, well, you can try to estimate from these observations that the sun itself, because it has such and such characteristic, is likely to explode in a certain number of days. And if you know the age of the sun, then you can say whether it will or not explode tomorrow with some probability. Okay? But okay, in most cases, you would say there is a high probability that the sun rises because it has risen for a lot of days that you observed it. Okay, and all these reasoning, in a way, are based on comparing with similar situations that occurred in the past. Either you compare the next day to the previous days, or you compare the sun to other stars, or yeah. So essentially, you always the natural reasoning, I would say, is to say in what sense what I have to predict is similar to what I have observed. Okay, another example is you can often find this in the IQ tests, for example. So someone gives you a sequence of numbers and tells you and asks you what is the next number. So often you can answer these IQ tests unambiguously or almost. So for example, okay, there are not so many numbers, so there can be many. I mean, you can guess that there can be many answers, and I give you a few of them here. So actually, there is even a website where you can enter these numbers, and it will tell you all possible, or not all possible, but a significant number of possible extensions of this sequence. So it's called the Encyclopedia of Integer Sequences. So if you enter 1, 2, 4, 7 on that website, you get 528 hits, which means you get sequences that all start with 1, 2, 4, 7, and that continue in different ways. And they are numbered, all these sequences. So this is the number of the sequence here in this website. Okay. So one of them here is the maximum number of pieces that you form when you slice a pancake with n cuts. Okay. And you can verify that every time you add a cut, you cut all the pieces that, sorry. So you have a pancake, you start to cut it, and you can every time cut as many pieces as there was, plus the number of cuts that already are. I don't know if that makes sense, but
Maybe if you drawing.
yeah. Good point.
Olivia, while you're doing that, this encyclopedia is loading as well because it's got 529.
Oh, so maybe there is a new one. Which one is it? So yeah, it keeps growing actually. I think everybody can add sequences to this site.
Maybe someone's added that it was used in a talk in Canberra.
Yeah. But okay, essentially the idea. I mean, you can check that. Maybe you can. It's fun to go to the website and to look at all these sequences. But the idea is that all these sequences, they have some kind of simple explanation of how to derive the next number from the previous ones. So this is one possibility. You constantly add n to the previous value, and you get this sequence. Or you do a second order recursion, and you get this. Or even third order recursion, and you get another continuation of the sequence. But okay, so this is one category of sequences, kind of recursively defined sequences. Another one, which is interesting, I think, is to look at the sequence as binary numbers. So you write these numbers in binary form. So you get this 1, 10, 100, 111. And you notice that there are always an odd number of ones in this expansion, right? So the next number after this one that has an odd number of ones is this one, and so on. And these are called the odious numbers, and they give this sequence. So I think it's important to see that there is a difference between this kind of continuation, I would say, like where you look at the numbers as they are given in the decimal notation, and you try to find how you can add them up to get the next sequence. And here you try to look for other type of properties, not additive properties, but I don't know how to call that, but I don't know, pattern properties. Like you look for patterns in the binary expansion. Well, okay, there are some other funny things that you can think of. Actually, this one is not in the encyclopedia, but because it's not exactly correct, there should be a 3 to make it correct. Because I just thought, okay, if you look at the decimal expansion of pi and e, and you can interleave them, so pi would be 3, 1, 4, 1, 5, 9, and e 2, 7, 1, 8. and whatever. So why not? I mean, it's also correct. It starts with 1, 2, 4, 7. So why not? And okay, you can invent all sorts of things. In general, in these IQ tests, there is one kind of natural answer, one answer that looks simpler than the other ones. Although all the other ones are correct, there is one that seems more reasonable. And the game usually is to try to guess what the examiner is thinking, actually. So, but there is no reason why I would prefer this version to this version, because I don't know, maybe my brain is naturally inclined to looking at numbers in binary form rather than looking at numbers in decimal form. It's just a convention. Like, we have been trained to look at numbers like this and make additions. But I mean, if you show this to I don't know, a 2-year-old baby, he probably would see the patterns, but he would not see the additive structure. So it's just a matter of what you are, I don't know, what you think about. Another one which is also funny, I took this example from Marcus Utter. Again, if you start with the prime numbers, so you write the prime numbers until 59, you enter this sequence in the encyclopedia on the web, and you would think that there is only one way to continue this sequence, is to put prime numbers. But actually, it's not the case. There is another sequence that starts exactly the same way, and which has a 60 instead of 61, which is the list of the orders of the simple groups. Okay, I will not tell you what simple groups are, but just to show you that, I mean, if you are a mathematician working on group theory, maybe you would immediately notice, looking at this sequence, that this is the sequence of orders of simple groups. So you would say 60, whereas if you are a number theorist, you would say 61. Okay, so it's also depends on your culture in a way. Okay, yet another example in the same flavor. You have a sequence of numbers again, and the goal is to extend this sequence of numbers. Well, if you have ever looked at the decimal expansion of pi, you will notice that it's actually the first numbers in the decimal expansion of pi. But if you have not seen that, like if I had put here some other maybe e or square root of 2, you would probably have not noticed it. So the question is, when do you notice a structure and when do you not notice a structure? Here you could say, well, let's just count how many times I have a 1, how many times I have a 2, and so on. And you will notice, at least if you continue the sequence for long enough, that actually all the frequencies converge to 1/10, right? And this is a funny properties of pi and e and some numbers like this, that actually every integer appears with the same frequency in that sequence, and even every subsequence appears with the same frequency in that sequence. Okay, so if you look at how many times 35 occurs in this expansion, you would have exactly 1 over 100. Okay. So you could say, well, it's just randomly. Like if I sample randomly integers independently, so if I just put numbers, I throw a dice with 10 faces, and I write down which are the numbers that come out, I could have a sequence that looks like this, at least in terms of frequencies. So why would this sequence be not random? Well, it's a difficult thing to say. It's not random because here we see a simple way to continue this sequence, and a simple way in the sense that we can express an algorithm that would produce this sequence and continue. And this algorithm would be the algorithm that computes the decimal expansion of pi. Okay, maybe it's not a simple algorithm, but at least it's an algorithm, and it's not just a random phenomenon. Okay? So that shows you that in this process, when we try to observe something and continue it or predict what comes next, usually we look for patterns or for algorithms or for something that we can express in simple and operative terms that would produce this sequence and continue it. So the question naturally is there some kind of unique way of doing this? And I think I have convinced you, I hope I have convinced you that it's not the case. And there can be many answers to such questions. For example, if you think in terms of algorithms, if you have a programming language that has some primitive that allows you to naturally make multiplications, additions, and so on, maybe expressing the algorithm that computes the decimal expansion of pi is simple, and you can write a short program that does it. But if you don't have these primitives in your language, I don't know, if you have maybe a Prolog programming language or some funny language that doesn't have arithmetic primitives, then you might have a much harder time expressing this program. And maybe you would try to create a program that expands or continues the sequence in a different way than computing the decimal expansion of pi. Okay, so it's all a matter of what are the things that you think are simple and what are the things that you think are complicated. So like this example of group theorists versus number theorists. So number theorists see primes everywhere. Group theorists see groups everywhere, right? So it's just simplicity is not an objective notion. That's the key point. So unfortunately, and this is, I would say, the main thing to remember about this is that there is no principle for induction, unfortunately. So I could just stop the lecture now, but I will continue a little bit. And whatever reasoning that you might think of to justify induction based on simplicity can just fail, because simplicity cannot be defined in an objective way. So what can we do? So now I want to talk a little bit about probability, because probability is often used in this context to justify induction or to derive algorithm for induction. And I want to tell you a few things about probability, just to have a common understanding of this. So probability is a nice theoretical tool or mathematical tool for dealing with reasoning with under uncertainty. It allows you to formulate imprecise statements in a way. And at the heart of probability, or at the core, there are these axioms. So from these you can deduce more or less all the rest, all the other properties of probabilities. But the question is, how do you relate these abstract mathematical objects that are the probabilities to the real world? How do you measure these quantities? Do the probabilities actually exist? What do they mean in the real world? And there are several answers to this question. Actually, it's, again, somewhat philosophical, this question. And there are at least 3 different points of view on how to answer this question. One very classical one is to adopt the frequentist point of view. And in this point of view, probabilities are just taken as limits of observed frequencies. So you throw a dice a certain number of times, you count how many times it ends up on 1 or 2 or 3, and you do that enough times until the frequency that you have converges to some value. And you would say the probability that my dice lands on 1 is this frequency. Okay? Then there is the objectivist point of view that says that essentially probabilities are intrinsic properties of natural objects, say. So a dice has an intrinsic probability of landing on 1 or 2 or something. And this intrinsic property can be measured via experiments, maybe in the frequentist way. You throw the dice several times. And at the other end of the spectrum, there are the subjectivists who say probabilities do not exist at all. It's just something that is in your mind. It's just some belief that you have about how likely the dice is to land up to land on a specific value. And okay, so the next slide gives more details about this, and I already told you. So the frequentist interpretation is that you measured how many times some event occurred as a number of as a function of the number of times you repeated the experiment, and you take the limit of this ratio as the definition for the probability. The problem with this approach is that you often cannot do repetitions of your experiment. So for example, if I tell you what is the probability that the sun will rise tomorrow, the 16th of February, then you cannot, the 16th of February 2006, there is only one such day, so you cannot repeat this experiment. So you cannot really define what is the limiting frequency of the sun rising on this specific day. So now, you can still say, well, even though I cannot measure it, maybe it still exists, this probability of the sun rising tomorrow. Maybe it's an intrinsic property of the sun itself, that's tomorrow it will rise or not. So that's a matter of believing that the physical system itself has this property. And some people do not want to make this, do not want to believe in that, and they rather say, well, probabilities are not something, the probability that the sun rises tomorrow is not something, a property of the sun itself, but a property of someone talking about it. Oh. It will not let me alone. Sorry?
So why not you remove it?
Yeah, I could. Well, maybe in the break. Okay. So an interesting thing is that we have seen these properties, these axioms of probability, and it happens that if you try to formalize what it means to believe with some degree in some events, so you try to define a function, the belief function, that assigns number to events, and you try to ensure that this function is kind of rational or corresponds to natural intuition about how you would combine belief degrees. Then if you do that, you will end up with the same axioms as the ones satisfied by probabilities. So you could very well say degrees of beliefs satisfy the same properties as probabilities, so maybe probabilities are just degrees of belief. I mean, there is no way to tell between them in a way. Another thing about probability is the famous Bayes rule. So from the previous axioms and from the definition of conditional probability, you can derive this rule that tell you how you should update probabilities or degrees of belief, whatever they are. So whether you're objectivist or frequentist or subjectivist, you have certain probabilities before observing the data. You observe some data, and you want to compute the new probabilities after having observed the data. Well, a natural way is to use this Bayes rule. Okay? The only thing is that often the prior probabilities cannot be defined in a frequentist way. Like the prior probability that the data is generated by some function cannot be defined in the way that you can measure the frequency. Like you cannot repeat your experiment. Usually in learning problems, you have a learning problem. You can you can maybe get more samples, but you cannot get more problems. You just have one problem. So in this sense, the probability that the function, that the target function is some function h is more a degree of belief than a frequency. Okay, but it doesn't matter because these rules, they just make sense in themselves in a way. But it doesn't mean that because these rules make sense, using them will give you a good induction system, or rather, it doesn't imply that you can justify using these rules. And that's what I say here. It doesn't prove anything that you have used probabilities. So if someone comes and tells you, well, I have a very nice algorithm for learning that I derived from the very rigorous statements in probability theory, and I have used Bayes' rule, and I have used this and this property of probabilities, so it should work. Well, that's not the case. It's just a nice way of reasoning, but it doesn't prove anything. Okay? So it doesn't mean you should not use them. You should, because it's convenient, but you should not expect that by using them, you will get something which is better than by not using them. Okay? So, okay, I'm kind of repeating the same ideas again and again, but with slight variations. So, if we come back to what we mean to to make predictions or to generalization, it's kind of obvious if you look at it that if you want to be able to predict something, you need to assume that there is some kind of relationship between the future and the past, or what you have not observed so far and what you have observed so far. Okay, that seems trivial to say this in this way, but but what is not obvious is that this implies that there is no general mechanism for learning, and every mechanism for learning is specific in the way it makes assumptions about how the past is related to the future. So the question now, having said that we need assumptions, the question now is how many such assumptions do we need? Like I said before, I gave you this example of relativity in physics. It's nice to have a few assumptions, or as few assumptions as possible. And it turns out that we can kind of almost avoid completely assumptions about relationship between past and future if we are in a setting which is called the competitive settings, and I will give you a more precise statement about what this means. And the point is, we can always take two different points of view. One is we make assumptions and we say, well, under these assumptions, what can we do? What is the best thing that we can do, right? And here we can prove things. We can provide mathematical statements of what this means. Like once we have fixed the assumptions, we can derive kind of what is the best algorithm under these assumptions. But we cannot justify the assumptions. Another thing we can do is we avoid completely assumptions, but instead of trying to do the best we try to match the performance of someone else. So I give you a few algorithms, and the question is not to build a better algorithm, is to do at least as good as all these algorithms, or the best of these algorithms. And in this case, you can prove results about how you match the performance without making any assumption on how the data is generated. So now I come to the possible scenarios in which you can perform learning. And this is not an exhaustive list. It's just a few examples. And actually, we will just focus on one of them. So I don't know if everyone is familiar with all of them, but okay, the offline supervised learning scenario is the most classical one. You have training data with labels, and you try to build a function that predicts the label of new data. The semi-supervised learning framework, I think someone talked about it yesterday, was it? So you have training data with x and y's, and also unlabeled training data where you only have the x's. And you want to, again, produce a model that will predict the y's of your x's in the future. The transductive is slightly different. Transductive framework is slightly different in the sense that it is not required that you build a model. It's just required that you make predictions. And you are given in advance the points at which you will make the predictions. The online learning setting is somewhat an iteration of the transductive setting. I give you a number of labeled instances, and then I give you one new instance without the label, and I ask you to predict the label of this instance. And then I repeat. I give you another instance, ask you to predict it, and so on. Okay? And you can have several variants going towards, in a way, towards reinforcement learning, where instead of making predictions, you have to take actions, and you get reward. And you may also get reward only at certain times, and you may have partially observable reward in a way, or errors, and so on. Okay, so why do I talk about this? Because I want to show that there is a distinction. And I think, again, this is important because somehow it's often the case that people mix all these things together. So let's say, for example, when people talk about Bayesian inference, they mix something which is assumptions about how the data is generated with something which is an algorithm, and with something which is a type of analysis of algorithms. And I want to make clear what is the distinction between all these notions. So I give some names here, and I try to explain what they are. So one thing is what you assume about how the data is generated. And this is only useful when you want to prove theorems, in a way. So it doesn't imply anything on how you should build your algorithms themselves. So you can build an algorithm, and it can work no matter what you have assumed on how the data is generated. So like, people tend to make some kind of distinction between, like, there are the frequentists and the Bayesians. The Bayesians use Bayes' rule all the time, and the frequentists, they use some funny other techniques, and they rely on the IID assumptions. They assume that the data is IID. So what happens when it's not IID? So again, this is mixing everything together. And the fact that the data is IID or not does not matter for the algorithms themselves. They don't care. They get the data, they try to build a model, and hopefully it's correct. Or it does a good job at predicting new instances. And maybe not. And the way the IID assumption, for example, is only relevant when you want to prove things or make formal mathematical statement. Okay? The protocol, which is the way you give the examples to the learner and what you ask the learner to return you, that's important for the learning algorithm. And that's maybe the only important thing for the learning algorithm. So you would probably build differently a learning algorithm in the online learning, or in the semi-supervised learning setting, or in the offline learning setting. Okay? The success measure, that's how you measure the quality of the output of your algorithm. Okay? And sometimes it's kind of a theoretical quantity. Like in reinforcement learning this morning, we saw the expected reward that we obtain, the discounted reward, for example. That's something you cannot measure, because you would need to have all the future instances. But it doesn't matter, because you know that you can approximate it in practice. Okay, and again, it may serve as a guide for designing algorithm. You know that your algorithm is trying to go in the direction of maximizing the reward, but you know that it won't maximize it exactly because you cannot measure it. Okay. Then comes the type of analysis that we make of all this. So given a data generation mechanism, given a protocol, a success measure, and an algorithm, what kind of things that do we want to prove about this algorithm? And we can have more restrictive assumption on the properties of the data or constraints in the problem that we have that allows us to design this algorithm. Okay. So now, again, same thing again. So if you have a learning algorithm, it can perform very well in various different settings. So you can have IID or online or whatever, and still the algorithm will do a good job. And this shows you that somehow there is no reason to relate the algorithms to the settings. And that's, I think, the important message here. Okay, so now I'll give some examples of each of these things. So the data generation mechanism, the protocol, and so on. So, okay, as I said, data generation mechanism, these are assumptions that you make about how your data is generated. One, I would say the most restrictive assumption is to assume that your function was sampled from some distribution, and then your data was sampled from some distribution and labeled according to that function. So that's kind of the hardcore Bayesian assumption.
I mean, I also like to think of Bayesians this way, but they wouldn't think of themselves this way. They wouldn't say the function is sampled. They would just say, we don't know the function.
Right, yeah.
So we express our not knowing the function by the prior.
They would say the prior is the degree of belief, right? But sure.
Yeah. I agree with you.
But you like when you do the analysis, that's where these things are useful. When you do the analysis, you will make statements about the error on average under the sampling of the function according to the prior. And that's where you mix kind of the Bayesian and the frequentist point of view. Okay, the IID setting is you don't assume anything about your function, but you assume that the data is sampled from a fixed distribution in an independent and identically distributed way. The transductive setting, the data is fixed, and what is random in a way is how you split the data into training and testing. Okay. Then there are some flavors of online data generation, whether you assume that it comes from a random source or whether you assume that it's deterministic. And this gives several different versions. Okay. The protocols, as I said, there are essentially two directions, the offline protocol and the online protocol. And also the difference may be in what information the learner is given. I don't give more details. Success measures. So actually, I talk about success measures, but these are more loss measures. So it's the opposite. There are two ways, more or less, if we forget about the third one, to measure the loss. One is to measure the loss on average over the future instances to be observed. So that's the expected error. But for this, you need to assume that there is some kind of probability for generating the instances. And the other one is the cumulated error, which is relevant in the online framework. So you get a new instance, you predict the instance, and you suffer a loss from not predicting correctly the label. And you repeat that, and you count the sum of all these errors. And that's called the cumulated error. Okay. Now, I think it's the fourth topic here is the type of analysis. So again, there are more or less three distinct versions. One is the worst case analysis. So you say you try to estimate the performance of a learning algorithm under the worst possible conditions. or the worst possible generation of the data. The average case would be you take the average performance of the algorithm, so the average loss under various possible data generation mechanisms. So for example, in the Bayesian type of analysis, you would take an average under the sampling of the functions according to your prior. Or there are the so-called this case analysis, which is supposed to focus on the specific problem at hand and not making assumption about what is the worst case.
Do people ever care about best case analysis of the algorithm?
Well, actually, I think there is something like this in computer science. There is some best case analysis. Not sure exactly, but I would say in learning, it would be a bit too optimistic.
If you condition on the data, you can get away with something like that.
Well, but then you're more in the this case analysis. So you're not trying to say, I mean, best case would be maybe
You're right.
yeah. Sorry.
I think I would like to comment about this success measures because you sort of focused on expected error.
Yes.
Now, in my view, having large error is not necessarily a bad thing. Random guessing is a bad thing. So anything which is far from random is okay. And in anti-learning case, which we had taught previously, you have a situation when you have you could prove that you will have very high errors.
Yes.
But this is consistent high error, so you reverse decision, you are okay.
Right. Right. Okay.
So,
Yeah. Okay. It's true. And actually, well, later on I will show that what I'm interested in is more the difference between the error of your algorithm and the error of some other algorithm. So this other algorithm could be the random guessing algorithm. So in this sense, you could have high error but still be good in the sense that you're close to some, or you're at least, you're far from random guessing. Yeah, but okay, I'm not taking this inverting the signs point of view. Yeah, okay, maybe I should add it. Also. Okay.